some introductory material from a few of us here, and then there will be the main event from Navid, and then there will be a reception afterwards. Restrooms are in the back left. The reception will be inside. You can go in and out, but it might be pouring rain. Anyway, so thank you all for coming. So we're here for the Sean Haney Memorial Lecture. The Sean Haney Memorial Endowed Lecture was established by Sean's family and friends to honor his memory as a scientist, friend, surfer, cyclist, and student. Since 2023, the fund has sponsored events at Scripps, including an annual public talk. Every year around Sean's birthday, which is tomorrow, Valentine's Day, the lecture teaches us about observations and fundamental insights into the topics that inspired Sean: waves, upper ocean turbulence, and nonlinear dynamics across scales. This annual gathering honors Sean's memory by deepening what Sean cherished: knowledge, friendships, adventure, and community. Thank you all so much for coming. And now I'm going to pass it over to Sean's brother, Seth.
Thank you. Sean spent most of his life here. Oh,
I'll show this.
oh, right. Thanks. Sean spent most of his life here in San Diego. He grew up here in La Jolla. He went to undergrad at UCSB and grad school at UC Boulder, University of Colorado Boulder, where Baylor Fox-Kemper was his PhD advisor. There he studied physical oceanography. He came back to SIO in 2015, where he worked with Bill Young and Jen McKinnon. Sadly, in 2018, he developed a neurodegenerative disease that he later died from in 2021. But the people and the work at SIO made a large impact on Sean, and it seemed, and by the attendance here and the support that we felt, Sean made a big impact on them as well. Sean was an overly friendly and exuberant person who was always wanting to share his pure sense of adventure with anyone who would join him. He loved biking, surfing, hiking, and adventures. And he made a really close-knit group of friends here, friends who have been incredibly supportive to our family to continue his memory. As his older brother, early on, I was in the position where Sean was trying to keep up with me because our 4-year age difference made a big difference in terms of what we could do. But very quickly as an adult, that relationship flipped, and I spent a lot of time trying to keep up with Sean and all the adventures that he would do, and keep up with Sean in his quantitative science and math skill set. Sean, I always saw in Sean the things I really wished I could be. Many of you know that we lost my mom and Sean's mom a few months ago. You can see on the screen a picture of Sean and my mom together. Our mom was a deeply loving and caring person with an unbelievable, infinite patience to deal with the 3 budding egos of me, Sean, and my dad. She was a caring and wonderful person, and she will be sorely missed. Mom and Sean both died of degenerative neurological diseases that may have been impacted by tick-borne infections. So I want to say, please be careful when you're enjoying the outdoors, wear insect repellent, and always check for ticks when you get back. So in closing, we, the family of Sean Haney, would like to extend our sincerest thank yous to all the people that have been involved to put this event on, specifically Jen McKinnon and Nicole Quoto, but also a huge thanks to Sean's friends from the greater SIO community, or that were once here at SIO. That's Greg, Till, Ben, Amy, Nicole, Navid, and so many more. You all do so much to keep Sean's memory alive, and I really can't express how much it means to us, everything that you guys do. So finally, I just want to make a comment about the shirts. the Hawaiian shirts are here to commemorate the talk. Sean was a big fan of Hawaiian Shirt Fridays. So please grab a shirt. I see some people are even wearing previous year's shirts, which is wonderful. Grab a shirt in, just behind me on the tables, and wear them in Sean's memory. So I think I'm going to pass it off now to Greg. Thanks.
I just wanted to say thanks. It means a lot to me to be back here every year. So my job is to introduce Navid, my friend. And Navid is this year's speaker for the Sean Haney Memorial Symposium 2025. Navid Constantinou was born in the suburbs of Nicosia on the eastern Mediterranean island of Cyprus. He was raised on halloumi and sunshine. He received undergraduate degree and a PhD in physics from the University of Athens, where he also established himself as a photographer, soap maker, friend of artists, and an inquisitive, sensitive soul. After getting a PhD, he came to Scripps on a NOAA Climate and Global Postdoctoral Fellowship, NOAA Climate and Global Change Postdoctoral Fellowship, to work with Bill Young, where he studied turbulence over topography, surfing, and met Bill's fellow postdoc, Sean, a few months after Sean himself arrived in 2015. Navid and Sean shared an office, and it was Sean that took Navid out on his first surf session at Scripps, which established a lifelong love for Navid. First surf session and countless more. Okay. Navid and Sean, so I think Navid and Sean have a lot in common. This is my perspective as good friends of both of them. And I think something that they both shared, which is a rare quality, and is their capacity for empathy and caring, loyalty to friends. After leaving Scripps, Navid adventured across Australia and around the world until he found his current home as faculty at the University of Melbourne in the School of Geography, Earth, and Atmospheric Sciences. And now I'm going to leave it to Till for a short anecdote before Navid gives the talk.
I just wanted to fill in one more thing. I remember very acutely going for a long bike ride with Sean and Greg, and no matter how hard the bike ride was, they would always start talking about some arcane physical oceanography problem, like the most technical details, and I just couldn't keep up. So the only thing I could do is pick up the pace to try and shut you guys up. But I do have another funny connection between Navid and Sean, and this is something I dug up from 7 years ago. So, okay, I should preempt this by saying that Sean is one of the very few scientists who has a 100% funding success rate from the NSF. He wrote one proposal and it was funded. And that wasn't the only proposal he wrote, because he also was a funding body. And so I at some point we tried to write this proposal. It was called Decadence, Discovering East County and Delicious Exhaustion. Navid, Till, Sean. It's a nice acronym, as you can see here. And the idea was driving to East Coast, going for a ride, run in Pine, come back, and it's got a lot of detail. You'll see, like, we really put the work in here. And then Navid said, I like the first draft. I'm skeptical about the weather. Navid Constantinou does not have a record showing enjoyment in biking wet conditions. What is the actual weather forecast? And then our funding body, the PO, Sean Haney, responded, I have now received all reviews, and I'm pleased to say all reviews were good to excellent. However, all of the reviewers have expressed concerns with the lack of detail in the risk assessment. As such, I have granted a preliminary allocation of the funds necessary to complete this project. Disbursement of these funds is contingent upon receipt of a more detailed risk assessment plan and/or change in the planned dates of the proposed fieldwork if possible. If the dates are to be changed, a detailed risk assessment plan will be required for the new dates. Congratulations and thanks for applying to SFN. Sean funds nothing. That isn't fun. Sincerely, Dr. Sean Haney. And I just feel like he's still funding us, and he funded us today. And so even though he's not here, it's my great pleasure to introduce Dr. Navid Constantinou. Thank you.
Oh my God. I thought it would be easy. It's not really easy. I thought I wouldn't be emotional. Now I'm quite emotional. I forgot about what I'm going to talk about, all these things. Yeah, hopefully the slides will remind me. How do we hide these things? Hide, meeting. Yeah, I do this all the time and still don't know how to do it. Anyway, we'll put this here. Thank you. Thank you for having me. Thank you for this great interaction. I had forgotten this email. It's good to remind these like shenanigans. It's my great pleasure to be here amongst all of you friends. This is like the best reunion ever. This is my best conference like in the world. Yeah, so, all right, I'm gonna talk. I put this title on. They were pressing me for a title, and I said, okay, I'll put this title on. Make sure you put the emoji there. The emoji is part of the title, I said. Waves of the future. So I'm gonna try to talk to you how I think, and at least a few other people here in this room, I think we share the same vision that somehow software and science should go hand in hand. They go hand in hand, but people usually ignore it. And then I'll try to tell you to showcase how, I'll try to make a case for how that should be and how that is changing. And, you know, how we could have like models that can do a lot of stuff together, fun stuff. This is a simulation of stratified turbulence that I made with a model that we've been working on with my friend Greg here, friend, collaborator, everything. So before we start, I'll show you this animation. This is a video going backwards, so don't get too agitated with the physics. But yeah, so let's say, all right. All right, so what I'm gonna talk about today? I'm gonna talk a little bit. So it's a wide audience. It's a really wide audience. A public lecture, and then we have like professors of oceanography. So I'll try to entertain you both. My main hope is that I entertain you and that you're not bored, and then you learn something. That's what I hope. So I'll try to talk about why climate is a little bit of a difficult problem, and then why we have some people like would know about that. Some people might not know. I'll try to bring everybody on the same page. I'll talk a little bit about climate models, ocean models, and you know where they started, where they are now, and then I'll conclude with how I think modern software, if done correctly, can have a big impact on our workflow, whether we are researchers, teachers, or just want to have fun and learn stuff. So let's start with the first one. Okay, why climate is a bit difficult. Okay, climate is the statistics of weather. So it's not just about predicting what the weather will be next week. It's about predicting what the statistics of weather will be the next few years, few decades. So that's one thing, just to put things in perspective. So I want to start with this figure. It sounds complicated. We'll break it down. There is a very big committee from scientists all over the world. It has this pompous name, the Intergovernmental Panel on Climate Change. And all these people meet and they use climate model results and science from all over the world, and they write a report and they give it to governments. And they suggest what they should be doing about climate change. Some governments follow it, some governments don't. Anyway, I don't want to get into that. Now, this figure comes from that report, this last report. It's called the AR6 report. And it shows the following. It says, compared to pre-industrial revolution, all these lines show what is the global average surface temperature, the warming that we will be experiencing. And all these are results from climate models under two different scenarios. One scenario, these orange lines, are what we call the high emission scenarios, the scenarios where we all as a humanity decide to do nothing about climate change, just like this business as usual. We keep burning fossil fuels and whatnot. And so this is the high emission scenarios. These are all these orange lines. And then with the blue is the same collection of models when they run it with a low emission scenario. Say we all follow the Paris Agreement and we all reduce our carbon emissions as agreed. And so here we are, in 2025, around at 1.5 degrees warming. If we ask from this graph, when are we gonna cross the 2-degree warming? We can see that some of the blue models, the models with the low emission scenario, cross the 2-degree warming earlier compared to some of the models with a high emission scenario. This seems counterintuitive. And there's a big spread. That's what I'm trying to show you. Do we see the mouse? No. Anyway, I'm showing you here. There's a very big spread about all these different climate models, how they're predicting the warming. There's a very big uncertainty in climate projection. So, but why is that? Why is that? That's what I'll try to explain a little bit. This is what we mean by climate projections are uncertain and it's hard. Yeah, it's because we cannot narrow down these predictions. So just to take a step back. All right, what's happening? Oh, great, thank you. I still don't see it. Okay. So what sets the ocean and the atmosphere in motion? Okay, what sets the climate in motion? So in very, very simple terms, sun shines and it brings a lot of energy through radiation in the tropics mostly, all right? And then somehow this heat has to be transferred away from the tropics and go towards the poles, because otherwise, if you go to the tropics, it would have been boiling water or something, because the sun has been doing that for quite a long now. So this sets the atmosphere in motion. This sets all these winds that we see, all the wind patterns, the jet streams. It sets also the ocean in motion. And these motions act to carry heat away from the tropics and towards the poles. And then when this happens, and then most of this energy, or all of it, is radiated out. So if whatever we get in is exactly equal with whatever goes out, then we have a steady climate, a climate in equilibrium, and we are all happy and jolly. If what comes in is not exactly what goes out, but there's a little bit of a leftover, these little purple bits that come back in, teeny weeny bit of a leftover, then we have climate change. Okay, and to put some numbers, so what comes in instantaneously on a sunny day, not like today, on what you usually have here in Scripps, except today, instantaneously we may get from the sun, perhaps actually this number is around the tropics, 1,000 watts per meter square. And I admit that to me, this number means nothing. I have no intuition about this number. But to put it in perspective, this teeny, teeny, weeny purple bit that is climate change is 3 to 5 watts per meter square. So if we're trying to predict climate change, we have to be able to predict, something with good accuracy, a 3 out of 10. So that's part of the difficulty. It's a little bit residual, this climate change signal, but we've been doing it for 80 years now, or 100 years, so it adds up. So if you want to be more quantitative in the room, if we have here, it's the same figure, but like, us coming from a climate model, this is the energy coming in from the sun, the short wave, as we call it. This is the energy coming out from the Earth, the long wave radiation emitted out, and their difference, we see that it's red. Where it's red is where the planet gets more energy than that it radiates out, and when it's blue, it radiates out more energy than what it gets in. If you sum up everything here, because this is from a model with the pre-industrial conditions, you'll get 0. If you do the same thing now and you sum up everything, you'll get 3 to 5. All right. Very small residual. So the climate is a hard problem because the Earth is very, very strongly forced. And then what happens when all this sunshine, this 1,000 watts per meter squared shine, then all these things sets a lot of things in motion, sets the atmosphere in motion, sets the ocean in motion. And then all these complicated turbulent patterns, here you see the motions of the atmospheric humidity, which kind of like shows you how the atmosphere moves around. It's pretty mesmerizing and nice, but also it's difficult to model. Okay, it's nice to make movies, but it's difficult to model. So yes, and then all this energy has to be moved around from these atmospheric flows and from the ocean flow, and it goes to ice and to the land and everything, and then we have to compute correctly how much is radiated out and compute this 3 watts per meter squared. That's why it's hard. And the Earth system, it has a lot of components, a lot of different components. So there's the atmosphere, there's the ocean, there are clouds, there's the trees, the biology, the land, there's ice sheets, and all these components interact intimately with each other. They exchange energy, momentum with each other, and we have to be able to model everything quite well in order to compute this small residual. Now, on top of that, for some of these components, we know the underlying laws that govern them. So, for example, for fluids, we know how fluids work. But we cannot resolve everything. We cannot have a climate model that resolves all fluids motions or the ocean motions down to a centimeter. So there's some approximations being done there. For some other parts of the components, we don't even know the equations. We don't know exactly what are the laws that govern, like, energy exchange of trees with the atmosphere or whatnot. So we have to approximate those also. So we use a lot of approximations. That's the bullet point of this slide. And for things either that we cannot resolve because we don't have the computational power, or for things that we don't even know the laws that govern them. And these approximations is what makes all these models diverge, part of what makes all these models diverge, and what makes predicting this small residual climate signal hard. Okay. Now, just to showcase the complexity of all of these things, if we only focus in the ocean, forget everything else, just if we only had the ocean, that's also already hard, because the ocean has motions at all scales. It has, from turbulence, to the scales of meters or centimeters that vary at time scales of minutes, up to things that vary, across the whole Atlantic basin, and they change at time scale of decades or centuries, and everything in between. What you see here is the surface currents from the biggest ocean simulation ever run, and I'll have it play. And you can see part of this thing. You can see eddies, you can see currents. You cannot see the overturning circulation because that we have to go underneath the ocean to be able to see that. It's like a 3D circulation. But you see all these things. You see waves across the Pacific. You see all these currents and eddies, which are almost don't move because the simulation is really short. You see tides here. You see very clearly the tides twice a day. You see, you see the ACC, like the Antarctic Circumpolar Current, this big current that it's a huge river of water that flows around Antarctica. And all these processes, we have to understand together, and how they interact together, and how they exchange momentum and heat between them, and how all together manifest in transferring heat from the equator to the pole, to the poles. Then that's only for the ocean. Okay. Now, there's another important like feature that that fluids have. When fluids are turbulent, like the type of, similar to how your bathtub or your cup of coffee when you stir milk is. These are all turbulent fluids. So what I'm showing you here is a snapshot of the ocean. It's a snapshot of the same simulation I was showing you before. What you see here in red and blue it's a quantity we call vorticity. It's just the tendency of the fluid to rotate either clockwise or counterclockwise, depending if it's blue or red. This is the South Africa. And if I wrote it there in case you don't recognize it. But also there's a shark here. This is really sharky in South Africa. This is where there was this surf contest, and this Australian surfer got attacked by a shark, and it's pretty amazing. If you see him, he's like talking to a reporter half an hour later, and he's like pretty chill about it, like so understated. Like I was like amazed. Like I would have taken me 3 months to talk. Anyway, so you see all these flow features. And you see, like, for example, here, this is an eddy, and this is an eddy. And what you notice is that there's like eddies inside the eddy. All right, and this peculiar recurrent nature of turbulence, that is this self-similarity, and I'll let it play just so that you can, be mesmerized. We can have this as a screensaver almost all the time. And this is beautiful, of course. The sad part is that all these little bits and little details are not, they could be artistic and we can admire them, but they actually also matter for the big picture and for the large scale ocean circulation. So if we want to understand really and predict well what the ocean is doing, we have to take into account all these small little bits and pieces. And that's putting a lot of difficulty into the scientists and modelers. All right. Okay. So now I want to talk about how are we doing these things? How are we doing these simulations like the one I showed you? Okay, how are we modeling the climate? So it's pretty simple conceptually. Okay, it's a laborious task. So what we do is we take the Earth and we take the atmosphere and the ocean, either or both, and we split it into a lot of boxes, like a lot of boxes. Okay, this is just a visualization. Usually the boxes are much, much smaller than this. And then we treat each box as something that has a constant temperature, a constant flow. Everything is uniform within this box. And we go and apply Newton's second law, whatever we learn in high school, the fluids version of that, into every box. And we see what this box is going to do for the next second or minute or whatever. And we update all the values in every box. And then some boxes interact with the neighbors, and then they give a little bit of heat to the next box and whatnot. And then we do it again and again and again. It's so laborious. Like there's like 3, 5, 10 rules behind it, and then you just have to do it again and again and again, like every minute or every 10 minutes, and then you have to do it so many times for all these boxes so that you predict what the climate will be, how the ocean will be 100 years from now. And because we cannot do it, we don't have the, it will take us forever. We put these things in big supercomputers. All right, and here's a picture of one. It's like having 160,000 laptops next to each other. And so we ask every processor, okay, you deal with these boxes, the other processor will deal with the next 10 boxes and whatnot, and then tell each other what you found, and then do it again. It's pretty laborious conceptually. It's nothing too extravagant. It's just a laborious thing that has to be done over and over again. That's why we give it to supercomputers to do it. All right. A lot of the supercomputers, most of the supercomputers, I don't know most, a lot of the supercomputers are used for climate modeling and ocean modeling and climate projections. AI now also, Bitcoin also, but climate modeling is still up there. So how did this started? So I think it all started at GFDL. This is the Geophysical Fluid Dynamics Laboratory at next to Princeton in New Jersey. The first atmospheric model was this paper, like in 1965, all right? And they even published their grid. This is the actual number of boxes that they had. Okay, you can count them almost. It's 20 boxes times 20, something like that. These boxes are huge. Imagine, remember, like when we make a big box, everything within this box is constant. So we want to make these boxes as small as possible. All right, we cannot make them 1 centimeter because that's so many boxes. It doesn't fit in all the supercomputers. But these boxes were huge. And they only have, this is the boxes in the vertical, 9, 10 boxes. All right. But still, even with this, they got some results. And this is a very important paper. The first ocean model came a little bit after, like a couple of years after. They were all in the same building working, these people. I noticed that the first ocean model took 2 years to publish. This made me happy because at least when I, push something out with my friends and then it gets rejected and rejected, and then it takes 2 years, I can think, okay, Kirk Bryan and Michael Fox took 2 years. So, all right. And then came the first coupled model. This is the first time that they connected the ocean with the atmosphere, and that they found a lot of differences. So in the late 60s, this started happening, and these are the 3. Couldn't find a picture of Michael Cox. I don't know if anybody has. I would like to have it. I asked Stephen Griffiths, he couldn't have it. So this is like Suki Manabe, this is Kirk Bryan, and this is Joseph Magorinsky, who was the director of the GFDL. And for this work, Manabe got a Nobel Prize in 2021. No Nobel Prize yet for ocean modeling. So we know it's up for grabs. Okay, we don't. Now, like since the 60s, there's been a lot of models that developed across the country and across the world, usually in modeling laboratories like GFDL and other national labs, and in other equivalent labs in Europe and Australia, in Asia, in Japan, in China. And I want to make a small distinction here for how different models look like in this vague space that I created. So say on this axis we measure how complicated and realistic. More complex means more realistic, more physics involved are these models, and how do they scale? They can run on big machines, for example. And on this axis, we measure how flexible these models are, how we can play around with them, and how they are easy to use. Okay, so on one hand, we have all these models that have been running from all these national laboratories to make climate projections or to make numerical weather predictions. NOAA runs every day something and tells you what the weather will be the next few days. They're up here, like a bit hard to use, but they scale very well. They have all the physics in them. They're usually written in compiled languages like Fortran or C. And then there's another class of models that a lot of people in research and teaching use. These are idealized simple models. They're written usually in scripting languages that we can very easily interact, write something, do something, plot something below. This is not really easy to do with these models, but this is very easy to do with this sort of languages. But they're more idealized usually. They don't have all the physics. They don't have all the complexity. They don't, they usually cannot be run on these 160,000 core supercomputers. So, of course, what about here? Well, if a model is here, we just throw it away because it's hard to use and it's not even realistic. But the obvious place that we want to search is here. Can we have something like that? All right. Can we have something that is very easy to use, but also with all the, good features of these models? So previous axis was talking about user interface. And I'm going to try to argue that user interface is quite important. And now I'll make my case with internet on phones. Who remembers this or had any of this? Oh, I see some, yeah. And has been using internet on those. Oh, yeah, very rarely, perhaps. It was an adventure, right? To read your email on those. Then came this. This is like a little bit of a hiccup. I mean, I don't know. Sometimes I found this easier to read my emails or find this. I had to count, like, you know, my finger. I'm a small person, and still my finger was like five of these buttons. Anyway, and then came this, and okay, and I don't know if we ask. I'm trying not to make an advertisement, but I think it's pretty obvious to everybody when you know, people started using internet on their phones. It's when smartphones came about, and I think that my argument is that it was when user interface, like there was a dramatic change, and then it became much easier to interact with these devices. So this is the user interface of an ocean model. I'm not condemning it, all right? Like, this is what we call a name list for the people who haven't seen it before. Some people have seen name lists before or have like interacted with them, all right? So say we have an ocean model. This is from the manual of GFDL social models. This is written by Cox in 1984. Say we have a big ocean model, and we want to interact with it. We want to be able to change, you know, the value of the time step, or the value of the viscosity, or the value. So this name list came about, and it was a great achievement back then because you had this list of parameters, and you could change some of the variables. You know, only variables that had numbers as their values, or like a true or false thing. And this is great because this made much easier for people who were not into the source code themselves to be able to change something and then have their own model experiment on the side without interacting with the whole source code. Okay, this was, like, you know, can say the first user interface of an ocean model. This is how it looks today. All right, most ocean models that are in this upper left corner, still we interact with them with name lists. And I'm saying it's good, but I think we need a bit more, a way to interact with not just changing numbers. And I'll try to show you why, how this could become quite cumbersome. Say, this is a name list, I made it up, okay? This is like in my, this is a model which has, you know, I can change the number of grid points in longitude, the number of grid points in latitude, and I can say, do you want to force with the data set? I can put a true or false. That's great. We can interact with this. And then comes, you know, I don't know, a friend, a researcher, a postdoctoral advisor, somebody, you know, with these like scientists who have ideas and inspirations, and says, what if we change the forcing, and instead of that, we use this other one? What can we put, like just this simple forcing, like something called latitude? Can we do that? Let's do that and see what happens. All right. How can you do that with this name list? Well, actually, you can. Or you can do it if you go into the source code, or somebody has done it before. And then that's the way. If somebody has gone into the source code and written another piece of code that works for this type of forcing, then you can have this sort of name list. You say false here, and then there's another parameter somewhere in the name list. Usually it's not even below. There's like 100,000 lines of code here or something. And then there's like some other parameter which you set true, and then you can set the amplitude with some number. This is this Q0 here. There you go, it works. All right. So given that somebody has implemented this feature in the model at some point, and now you can imagine how this thing can, you know, like after a few years of people using this model, every time somebody has an idea, they do something like that. And this can like make this name list huge. And then, you don't really know what's happening. I've run into these problems personally, like trying to, oh my God, like I've had this true and this true. What's happened there? I have no idea. It's quite cumbersome. It can become quite cumbersome. Okay, what we would like is like, I don't know if you've used, who has used Python or Julia or MATLAB? All right, so if you've used that, perhaps this reminds you of that. So we want to, instead of having a text file, which we call a name list, and write all the parameter values, we have a little script that we're using in MATLAB or in Python. And then we have some parameters, and then we create a grid with takes these parameters as input. And then we can create an atmospheric object in a sense of a software type of object, which reads from a data set or whatever, or we can create an idealized atmosphere, say, this is like pseudocode, but you get the idea. And then this is an idealized atmosphere which had this idea of this researcher, and we can even change that and do it whatever we want. We can make it cos squared, sine, we can add something. It almost reads as math. And then we can create a model, and then we can run this and whatnot. So how about that? That sounds good. That like how do you say, expands the possibilities. All right. So we would like, essentially, like in following Sean's spirit and my spirit, this is my theology almost, everything should be kind of fun. Otherwise, if it takes too long and it's too cumbersome and it's, well, I don't know, I lose track. So if it's something like, if it's a headache, usually, I don't know if you have tried to run big climate models, but it takes a month or 3 weeks to set them up. You have to run them on a big supercomputer. You have to get access to that, first of all. And then you're missing a binary file. You have to go talk to this person who has it and their laptop. But like, it is a little bit of a headache, okay? And you can't really play around. It's like, this is how it feels. I would like to play around, take a piece out, put something else, and it feels that, no, it's so hard to do that. We cannot be doing that. No, you have to use it as it comes. Or if you want to play around, you have to go to GFDL and ask the people to figure it out. I don't know, something like that. We want to be able to play. That's what we would like to do. All right. It can be done. I think it can be done. All right. So why do we want to be playing? And, the Legos here are not just there for a reason. It's important that it's like plug and play like Legos, because we want, as scientists and as like, curious people we want to be able to ask questions and say, well, what if, I want to switch the Earth's rotation off and see how it looks? What if I want to change the boundary conditions, the forcing? What if I want to change the bathymetry, take South America out, or I don't know, close the strait between the Gibraltar Strait? What happens? I don't know. Scientists have these curious questions, and then it's not out of curiosity only. Like, we learn physics by pursuing this path. And what if I want to share what I did with others so that they can do it also? That's also part of the equation. So this gives me a little segue to talk about this last bit of my talk, about how modern software can allow this Lego playing. All right. So let's see, how would this unicorn ocean model would be? All right. Oh no, this is not my slide. I don't want this slide. I want to show you now. Ah! Where is it? Where am I? No, this is the slide. Sorry. This is what happens if you work on your slides just a little bit before you come. All right. So now I have to hide this thing. But I don't see my pointer. That's the problem. I have to hide it first. Okay, it's like a seminar in Zoom here. like 5 years in zooming, I haven't figured it out. Okay, so what do we want this unicorn ocean model to have? We want to be easy to install, and this goes to the, easy flexibility, easy to interact with, easy to take take things in and out, model components, forcing boundary conditions, and easy to run, easy to plot things. I've heard like back in the day, to plot something other than one-dimensional plots, to plot something, you had to fly in Anchor. I'm talking in the 80s now. You had to fly to go to Anchor with your punch cards and plot. It was so difficult. Okay, it's a bit easier now. It's not that difficult, but still sometimes you have to run in one language and then download it and analyze in some other language and plot it. It's not like so straightforward. But we also want to have state-of-the-art accuracy for climate projections. And then we want these things to be able to run on big machines so that we can do climate projections, and then that they are fast, because otherwise it beats the purpose. If it takes longer to make the climate projection than the climate projection itself, so if it takes 200 years to run to predict what the climate will be in 100 years, it's not good. Okay, so essentially we want to have our cake and eat it too. All right, that's what we want. Everybody wants that. All right, so I'll show you a little bit. I don't want to be an advertisement of this model, but it will be a little bit. So I want to show you an ocean model that has all these features. And here I'm showcasing you videos. I haven't even put labels or numbers, but just to showcase about how with one piece of software, you can do all these sorts of things. You can do direct numerical simulation, like where the scales here are millimeters. You can do large eddy simulations. Some people might recognize these pictures and might know where these things. This is like turbulence in the mixed layer, in the upper ocean, mixed layer in the top, 50, 100 meters. And this is like a typical baroclinic stability forming. This is free convection again in the ocean's top 200 meters. This is like 200 meters, and this is like, I don't know, 500 meters. This is a snapshot of a regional simulation. Again, this is like not Jervis Bay, J Bay with the shark. This is the tip of South Africa, I think. And we can also do this is a bit like I'm showing you a little bit of a global ocean simulation. And we can do everything with the same software. And it's not because it has a lot of ifs. If they ask you this, do this bit of code. If they ask you that, do this other bit of code. It's like essentially one piece of code. So this is called Oceanography. It's a great name, in my opinion. Some people hate it, some people love it. There's no in between. All right. It's fast. I don't want to talk about that too much, but it's pretty fast. It's like so fast. It blew my mind. It blew our minds, I think. It's developed as part of the Climate Modeling Alliance. This is a collaboration between MIT and Caltech and some other institutions to make a new climate model. MIT, most people developing the ocean component, this software and other bits of that are in MIT. And there are some people in University of Melbourne, me essentially. And it's mostly the credit should go to Greg, which you can find somewhere, and Simone. They are the big drivers here. And in particular for the user interface that I'm trying to put the argument here, it's all Greg's. Greg's vision is what makes this user interface what I will try to show you. So I'll try to showcase you 3 examples, like pretty different. They're pretty different physical examples. You'll see how, but you'll see that it would be, I'll show you how it will happen. But I'll show you how we can simulate 2D turbulence, baroclinic instability on the sphere, and then a global ocean simulation. And you can see how I'll try to showcase you how we can plug and play and take Legos out and in, and then without having to spend 1 month of learning how to set up the model from each one to the other. Okay. So this is almost real code. It's missing 2 or 3 lines, but I can show you this is how we can set up and run a simulation on 2D turbulence, decaying 2D turbulence. So we have like this, we can create a grid. We can give here the properties of the grid, the number of the grid points, the extent of the domain, the boundary conditions. I use here 2048 points because why not? This sounds a lot. And then we can give the grid to a model, a non-hydrostatic model. This is a model which has also gravity, but if we're in 2 dimensions, gravity is like not making sense. And then we can, initialize this with some random initial conditions, both u and v velocities. And then we can run it, and then we can compute the vorticity, which is an important quantity. It's this quantity that shows you how much the fluid wants to rotate in one direction or the other, counterclockwise or clockwise. You can see that here, this line, it's almost reads as math. If you know the definition of the vertical vorticity, is the x derivative of v minus the y derivative of u. And these are operators that act on v and u and compute these derivatives. And we can plot it, and here how it looks. And if we want to see a movie like that, it's also very easy to do. And because I don't want to just say that it's easy, I want to show you that it's easy. So we'll run it now. What's the time? I have 10 minutes. I have lots of time. All right. So then, anybody else wants to? No, okay. So then we're going to go and actually run it now. If I manage to get out of this slide. All right. This is the first public lecture, perhaps, that the Jupyter Notebook opens. All right. Oh my God. I don't have you. Let's do it. Presentation, full screen. Can we do full screen? Anyway, it's big enough. All right. All right. This is the, this has the code, the little bit of lines that were missing from before. So I'm going to run this on the CPU because my laptop doesn't have GPUs, but if you're on a supercomputer, you can do whatever you want. So I'll run it in smaller resolution so that we can see results. It's pretty quick. So all these simulations that I'm going to show you today, everything happened last afternoon. Okay. Me and Greg were at the house playing like these kids playing with Lego, and we made these things. Okay. So that's how it happens. So I'll run these things, and then we'll have, this is how the initial condition looks like. The mess, because I've just initialized it with random numbers. But 2D turbulence has this peculiar property to create these vortices which merge and then create bigger vortices. So now I'm going to run the simulation. Now I'm running the simulation. It will take a while, but not so much. All right, live simulation in a public lecture. Gonna run until 40. Don't worry. Okay, it's done. It's done. And now I'm gonna make a movie to see this vorticity. All right, it should appear here. It won't look as good as the one that I ran with 2,000 points, but it's pretty good. You get the idea. All right. All right, we learned something. You see, vortices merge. Now, somebody was asking me before, I got a text, can we do beta plane? So to show you how easy it is, when I create, it's like I'll put a Lego here. So I'll make this model with a Coriolis force. So it's as if I'm putting it on a sphere that rotates. Some people who know what beta plane is, perhaps, if you don't know, it's as if I'm putting it on a rotating plane. So let's say F. Let's do 0. All right. Okay. So I'll rerun everything. Now it's on a beta plane. See, it tells Coriolis beta plane. All right. The same initial condition. This is a random mess. Now I have to run it again. All right. I'm sorry. Somebody said I have plenty of time. All right. All right, let's see moving. Let's see how it looks now. You should see Rossby waves, whoever knows these things. You should see things moving to the west, you see? Things are moving to the west, all these are Rossby waves. Things have the tendency to align, all these vortices have the tendency to align. I didn't run it long enough, but you can get the idea. You can lose your whole day with this. Now you can start playing. It's because exactly it's so direct, you can start playing, oh, let me see this, let me see the other. This is what happens, especially when, I'm with my friends, I'm with Greg, we lose a lot of time watching movies like that, all right? So that's the idea, that you can play, all right? But also learn, it's together. All right, let's go back. Okay, I'm not gonna run all these other codes, but they don't take so much longer to run. So the next thing I wanna showcase is baroclinic instability on the sphere. All right. Not so much to showcase the physics, but to showcase that, like you can see, the code is almost the same. Now instead of a grid, rectilinear grid, I create a grid, latitude, longitude grid, and with some other parameters. But I create this grid and then I give it again to this model. I also create something, I use an equation of state. This is how I compute buoyancy. In the ocean, the density depends on the temperature and on the salt. So that's what I'm doing here. I'm creating an equation of state that takes into account temperature and salt and computes density or buoyancy, as we call it. And I give all this to a model. Okay, I give the grid, which is the latitude longitude grid. I give this buoyancy. I put some Coriolis. So this sphere is rotating. All right, this is a hydrostatic model. Hydrostatic free surface model is the model that we use in large scale ocean models. And then I initialize it. This is the initial temperature and the initial salinity. And you see the initial temperature it has some weird expression, all right? But it looks like that. There is a front, a meridional front. So it's warm in the equator, cold at the poles. And the salinity is stratified, just stratified. So this is a prototypical example of, if this front is strong enough, then this will become baroclinically unstable. A whole bunch of eddies and a whole bunch of turbulence will form here, and this will enhance and will allow more heat to be transferred to the poles. So now the poles are pretty cold, but if it becomes baroclinically unstable, they should become a bit warmer. This is like a typical problem that we learn in school, in grad course. And you see, you can set it up quite easily, and it almost reads as math. That's the idea. So I'll let it go. So you see the temperature initially, these all are surface fields. This is the temperature, and everything else is quiescent. There's no flow. This will be showing you the speed of the currents. If something forms, something will form. Okay, I didn't make it like, and this will be showing you the vorticity, this tendency of the fluid to rotate clockwise or counterclockwise. When I saw this yesterday, I got so excited. I was watching it all night. Look at how beautiful it is. So you see and you see now, some of this yellow has transferred down to the poles. This is the baroclinic instability transferring heat to the poles. You see a jet has formed here. You see all this, similar to what we saw in the beta plane. So you see all these vortices aligned here. And you see this is the big jet that formed. Also one in the northern hemisphere. Anyway, you can see how you can lose a lot of time. Like, oh, let's change this, let's change the other. How can we make it? Yeah, and then, you can sprung out a lot of research problems or a lot of movies to send your friends and whatnot. Now, almost the same. Okay, I'll run a global ocean simulation. So again, on a latitude longitude grid, I don't go up to the poles because it's a bit strange at the poles. I don't want to get into these details. But I load the bathymetry, the realistic bathymetry now, and you can see it here. You can see continents, and there's also mountains at the bottom of the ocean. And more or less the same. I just initialize it with the initial conditions from the echo state estimate. And I forced this model with a reanalysis, the GRA 55 reanalysis, some atmospheric product that is available, and I let it go. All right. And initially, there's nothing else. It's just the temperature and salinity. And you'll see very quickly currents, the Gulf Stream will start forming. You see here, after some initial shock, this is the Gulf Stream. All right. And this was run yesterday on a GPU somewhere, I think in MIT. It ran in like overnight. We put it before we slept. We woke up in the morning and we plotted it. This is at the quarter resolution. This is resolution that people use for science and publish papers. It's not this is not a toy. I mean, it's not like more toy than others. It's like as realistic and complex. Some physics are missing. I don't want to get into the details, but it's pretty up there to be able to run on one GPU. Essentially, in a Jupyter notebook, you could run it. It might take a bit, if you leave it overnight, perhaps. But if it was a 1-degree model, you can almost run it in a Jupyter notebook and see the results immediately, right? So I'm just trying to showcase you how this easiness, like this flexibility and user interface, trying to if you look ahead into the future, how it can transform the way we do research and the way we do teaching. Because we're doing a GFD class, we can put this as part of the book almost. All right, so what would we want from a modeling software? In an ideal world, we want to be able to switch model components in and out easily. We want to be able to modify forcing and boundary conditions. We want to have a code that doesn't need a bunch of comments, if possible. So it's almost a code that reads like math. And this is actual code from our user interface. It's not, I didn't make this up. I mean, something, I made it up, but it's with operators that exist. And we want to be able to share with everybody. So if I write this little script of 20, 30, 50 lines, then I can give it to you and tell you, run this with this version of the package, and it will have the same results. And we want to be able to plot easily. So when you work and plot and run the model in the same environment, that's so easy. And mostly, we want to be able to play together, all right? Because that's when fun and good things happen. So I'll close here, and some take-home message. If there's one message to take home, is that the ocean is very beautiful. It has all these turbulent patterns and all these mesmerizing patterns and all these self-recurrent properties, which makes the flow look amazing and draws a lot of attention for people and gets people to be passionate about it and want to study it. It's quite nice. Like I was trying to show you how the models, the climate models, the ocean models, the atmospheric models are our eyes to the future. It's the only way to predict the future at the moment. And as a society, we are called to make decisions. We are called to mitigate climate. And the only tools we have to make those decisions are climate models. So they are indispensable for society reasons, for research, and for teaching. And software and science go hand in hand. The past 10, 20 years, definitely. Everybody who is doing science codes in some way or another. But I think there's a much less effort put in making software better compared to making science better. And I would, I'm like, my thesis is to let's put more effort into that. I think it worth it. And I'll close with this photo. I took this photo near the south coast of New South Wales, where I was living before I moved to Melbourne. And it's quite cute, I think. It's also a little bit angry, I think. And I think it's angry because we don't put so much effort in software for ocean science or climate science. I think either or will make this happy. So I'll stop here. See you, Ben. All right. If you want to grill me with questions, I'm here. Yeah. We're working, not, they already know, we're working on it. Yeah. Hold on your chairs. You can do a lot of ocean science, ocean only science up to now, but yeah, we're working on that. I'll prioritize ECRs. Yes. I assume you are an ECR compared to Teal. Yeah. Hi.
And I'm not a modeler, so maybe some of those things where it seems like very easy plug and play for somebody coming from those things.
Yeah.
So for somebody coming from like 0% modeling, it's, I wouldn't say like still like super duper easy. I do appreciate all the work that you guys
Yeah.
do. These events. I guess I was wondering, obviously you guys are putting huge amounts of work into this thing that is more accessible than anything that has existed previously in this kind of world. Do you have suggestions for kind of like how to get to that point where you can do the plug and play?
Yeah, well, you know what happens? You're in this world and you're in this bubble. We're trying to like be empathetic and try to put ourselves in the shoes of other people, but it's hard. But if you wish, like, it would be very helpful if you sit with us now or some other time or via Zoom, and we see what is the wall that you hit, and we'll try to make it better. Or you can also, edit the tutorial and make it, like when after we talk and you figured it out, then you can make it also better, like more. That's what we're hoping. Yes. So yeah, let's do that. Yeah. Yeah. Gunnar. Oh, you're very welcome.
So you showed the spread in climate projection.
Yeah. Well, look, climate, atmosphere, the ocean is chaotic by itself. Even before we do any climate change, the climate is chaotic and the atmosphere is chaotic. So there will be some variability because the system has some internal chaoticness. So if some of the spread perhaps is because of that variability, okay. But then some other of the spread is because one model uses this parameterization, which is okay for this bit, but not okay for the other bit. So it's a little bit wrong there. The other model uses another parameterization, which is a little bit wrong there. So if we make models better and we reduce these biases that come from the approximations that we make, then we'll be left with the spread of the system itself. That's the hope. I'm not sure. I'm not saying that will happen soon, but yeah, that's the hope. So yeah, Till.
Wonderful talk. Thank you. You said you don't have all the physics, but you're not going to get into that. Could you get into it for a bit?
What would you? I meant I didn't have all the physics in that simulation, but yes. So what? We're missing CIs, which we're working on. I think that's it. What? Well, that we have. I didn't have it here. We have that. Yeah, I didn't have it here, but we have it. Yeah. So yeah, we have a tripolar grid. We can do we can do grids over the whole ocean. Just putting the pole singularities on Canada and Russia, as people do usually, put all the trash there. I don't know. I'm sorry, like the numerical trash is a metaphor. Yeah. Not sure about. I think that's it. I think that's it. These are almost all the ingredients to make an OMIP submission. It's like a submission for the CMIP, but only for ocean-only models, like that are forced with atmospheric analysis.
So you could see it replacing traditional ocean-only models?
Well, it's not that no model replaces the others. It's good to have model diversity always. So I don't think it will replace anything. I don't know if some laboratory decides to stop putting effort in their model and their model becomes, archaic after years. Yes, in a sense, it could be replacing that. It will replace in whichever model you're putting effort and you're developing it actively, that model will be alive and thriving. If you let the model go, then after a few years, it will go. So I don't know what are the laboratory directors thinking about, but I don't think it will replace all the models. Like if I had to put a guess. Yes, yeah.
Fantastic. I was one of the ones, who went through the painstaking journey of trying to understand these old codes like MIT-G7. But what I'm wondering about is when you're making this software, it's beautiful, right? It's the Jupyter notebook, new model. How about the software or package or wrapping for the existing codes? We have a lot, like I said,
Yeah.
variety of Ocean
Yeah.
right now, but they're not very user friendly. You cannot even change the topography easy. Or
Yeah.
input output sometimes it's kind of
Yeah, that would be great. I don't, well, I cannot do everything, but yeah, that would be great. But I mean, I've seen people doing that, like writing Python wrappers for using MIT-GCM, for example, or using MOM6, or like, there was a student in my institution, like was struggling a lot with configuring MOM6 to be doing some regional configurations, and they started writing a Python wrapper, and it ended up being a Python package. Like some people put effort on that, and it's I'm very happy to see that. Yeah. So yeah, it's happening. Yeah. The sad bit is that usually traditional academia doesn't value these things. So a student has all this pressure. Oh, I need to publish 3 papers to get a PhD. Do I spend 1 year doing this and helping everybody else? The efforts like that have gained in the much more longer run. So that's why people don't like it. Early career researchers are a bit discouraged. Nobody discourages them, but the system. So I would like to see like a little bit more of a institutional effort to value these things as much as science itself, so that then I think that will kick things off a lot. Yeah.
follow up that. I'm wondering how you in your group those values of good scholarly practices in your students, and as someone who has previously worked at Viva and come from that healthy background, now I'm a graduate student and my third code is garbage again. It doesn't matter. Putting things in other places or taking that time.
Yeah. Yeah, all right. I mean, I can see your point. If you're writing something for yourself, you say, oh, what's important is that it works, right? It's kind of like that. Well, so at least I'll tell you how things have, like when I went to Australia, I joined this community of ocean modelers, and they already had a big, good group community I joined and I was very welcomed in that. And part of like our philosophy is that everything is open. And then, if somebody's developing a code to do new science, they are equally, their contributions is equally valued. So then, like by doing that, and like it takes some years for this tradition to become a tradition, but like by doing that, then people are not yet afraid, like, yeah, I'll put the effort because I'll help you with the code development and the writing this new thing that you want. You'll do the science, we'll be both in a paper, we'll both get the recognition. So that's one way of doing it. It would be good if things like that, like efforts like in developing models would also be valued more from traditional academia. Like, I don't know, that might change as, I don't know, people that are value these things go higher up. I don't know how to do it. Yeah, don't know how to impose it. I know how to do it amongst my community, and that's how I'm trying to do it. Like, show that it's of similar value. Like if you develop a tool, without the tool, you wouldn't be able to do the science. So it's equally valued, the tool or the thinking or the inspiration to do the experiment. Yeah, everything values. Yeah. Yeah.
I was also wondering, since Oceanography is written in Julia, if there is any priority to make it possible to make the derivative of.
There is, yes, there is a priority. We have also working on that, like actively, like, yeah, yes. I don't know when it will be ready though. I know what you want to be able to take the adjoint. That's what that's what you're thinking, and do data simulation and things like that. Yeah, yeah, yeah. That and coupling is one of the top priorities at the moment, I think. Yeah. So just hold on your chair a little bit. You can do all this other science in between. Yeah. Yeah.
Okay,
All right.
well, let's thank Navid. Thank you very much.
All right. Okay. All right. So let's see.
Reception, I think, next door, right?